Let him complete, then you ask question.
Good evening all. Today I'm going to present Kelvin probe force microscopy, its principle and applications. Now, the Kelvin probe method was first proposed by Lord Kelvin in 1898, and it was first used by Nonenmaker after more than 100 years in 1991. In this measurement, we generally measure the topology as well as the contact potential difference between the conducting AFM tip and the sample which is generated due to the capacitance charge. So I'll come to the what is the contact potential difference. Here we generally do with the AFM tip, and in case of KPFM, the tip is above the sample, means there is a distance between tip and the sample. And in KPFM, we generally apply two types of modulation. One is AC modulation, which is VAC, and another is DC modulation, which is VDC. Now I will come to the contact potential difference. Now generally when there are sample and tip, they are far apart, there is no connection, then there will be no connection. So we know the work function is the difference between the energy of Fermi level and the vacuum level, and the who have the work function less, then from there the electron can travel to the other end. So now if we can bring them in a certain distance such that the electrical conductivity happens through tunneling, then there will be electrostatic attraction. This will be a capacitance type of attraction, and now they will try to come in equilibrium. So as they will come to equilibrium, the vacuum level will decrease from the tip, and because the electron will come from the sample to the tip. Now, as the vacuum level is decreasing, this potential is generally known as contact potential difference. Now, if we apply a DC potential, constant DC potential, which nullify this contact potential difference, then we will get the work function of the sample, and our aim will be the get this work function of that sample through KPFM measurement. Now, in KPFM measurement, as there is in contact with, not in contact means there is electrostatic force. The electrostatic force is dependent upon minus half dc dz into v squared t, but this capacitance, as there is two charges there in parallel, so there will be capacitance type of charge. So it is given as this equation. So which the distance, the capacity will reduce, and here the potential is given as DC potential with the constant potential difference, and there is a AC potential is there. So if we elaborate this equation, and if we take this as A and this is as B, so A plus beta square, so we'll get, we can write this as this equation, where FDC will be this square, and VAC vice versa will coming from sin square omega t plus cos square omega t, and the cos square omega t will come here from means it will cancel out from cos to omega t, and this is the 2AV term. And the constant potential difference is generally given as V means work function of the tip minus work function of the sample by electronic charge. Now, as the tip is constantly oscillating with a fixed frequency, then if this is a sample surface, then it is the position of the tip is going from this side to this side. Now, at this position, as the distance from the sample increases and the frequency is fixed, so somewhere there will be an amplitude change and it will get increased. So as it will get increased, then it will try to come in again in resonance, so it will come down, and by that way it will measure the surface of the system, and it will give the topography of the system. Like here, the distance is getting decreases, so the amplitude also get decreases. In the other case, here the amplitude is fixed, but the frequency is changing. As here the distance get increases, so the frequency also get decreases. And in the other case, the frequency get increases. Here it is a topography. It is a data from KPFM. From we get topography as well as CPD. Here we can see that the topography we are getting from these peaks are coming due to the row, and this in the CPD the peaks are coming due to the trough. Here the position of the CPD and topography is reversed, because the the CPD is only we are getting from the DC bias, and the topography we are getting from DC bias as well as the AC bias. And in CPD, means the constant potential difference, the distance is as the distance is changing, the potential is also getting amplitude is getting increases, so the peaks are we are getting here. Now the application of KPFM, like here, the energy band and carrier transfer dynamics analysis. Here we have taken a perovskite solar cell where this side is electron transfer layer and this side is hole transfer layer. This measurement is done. This is the KPFM measurement, CPD measurement without light. So we can see that without light, it is giving this type of CPD. Now if we shine a light with white light, then we can see that there will be charge and electron and hole generation. So electron will come to the electron transfer layer, and hole will come to the hole transfer layer. As electrons are coming to the electron transfer layer, the work function is getting decreases. As the work function is getting decreases, the CPD value is also getting decreases in the electron transfer layer, where the in the hole transfer layer the work function is getting increases. So means here, from here the electron, it is difficult to remove electron from hole transfer layer, so the work function is high in the hole transfer layer. So from KPFM we can see where the charges is high and where the charges is low through the potential difference. Also we can identify phase. We can identify the phase, means the impurity phase in XRD also, but where exactly the impurity is located we cannot say from XRD or ACM. But here, from here we can say this is the topography of the of MAPBBr3. Here the author says that the MAPBBr3 may break into methyl ammonium bromide and lead bromide. So and this is the CPD curve of the CPD graph of the of this material. Here there are three different potential difference we can see in this position. This scan in three different positions they have scanned, and they are showing that this position is matches with the MAPBR3. This position, the blue line, is for lead bromide, and this for dark region is for methyl ammonium bromide. And this is the overall measured data for the whole material. So in that material, all the these two impurity peaks are there, and we can measure the where the impurity peaks are there. So from here we can measure the exact position of the impurity. Also from the measured data we can identify and the band energy diagram. Like here the work function for this material is around 4.56 electron volt. And if we get the band gap and the electron affinity of that material, we can get the Fermi level of that material, and from that band energy diagram we can say which type of material is this. Is it p-type or n-type? Like here the MAPBBr3 is showing as p-type material, as Fermi level is close to valence band. Like MAPBI3 will show, means in the other paper I saw that it is showing n-type material, means the Fermi level will close to the conduction band. Also ion migration investigation we can do through this KPFM measurement. here here a sample is taken where this is without bias, so they are giving two bias. One is positive bias, positive to plus 2 volt, and one is negative 2 volt. After giving the positive bias, the electron and holes are getting separated, and they just close the bias, means off the bias. Then they taken the KPFM measurement at different time. Then we can show that see that electrons and holes are moving and combining each other and coming to an initial phase after 720 seconds. And in this measurement, they show one can identify from which position to which direction the electrons and holes are moving through this part, from positive bias to negative bias. So these are the up to this I can I have read for this KPFM. I have to read a lot more and I have to gain experience. So to conclude that also, yeah, after doping also we can see that how the Fermi level and band structure are changing through this KPFM measurement. So the KPFM measurement is a simultaneous mapping of topography as well as potential position, that is the CPD of semiconducting nanostructure. Also through the KPFM, we can measure quantum dots, organic solar cell, multi-junction heterostructure. Means in the heterostructure, in the interface, what is the potential difference we can understand. Also the grain boundary, we can identify how the potential is getting differences. So these are the references. Thank you.
Stop it. Let the questions stop. Yes. Questions now.
So, can you go back to the where they have shown the principles? Can you explain anything about the principles of
Which one?
Don't stop the recording. Don't stop the recording.
Which one?
tell us about the principles?
Okay. Generally, in this position, this is in non-contact mode. Okay. So this is the work function for the sample, and this is the work function for the tip. Generally, this tip is made of silicon. Generally, and as the work function of the sample is low, so if it get in contact, the electron will come through tunneling to the tip. Okay, like here it is happening. They are they are close enough to make that tunneling, and as their electron are moving, so there is a charge is generating, and as their charge is generating, there will be electrostatic attraction, and it will be capacitance type of attraction from attraction. So as the electrons also are moving, the Fermi energy will be in equilibrium. Okay, so as it is coming into the equilibrium, the difference in the potential of vacuum level will be there with tip. So this vacuum level differences is called constant potential difference. Now, if we apply a DC current such that we can make it to the initial position, so here they are in that distance, but the as the applied potential is equal to this constant potential difference, so it come back to its initial position. And as we can measure this, so we can measure this also, because these are equal. So by this we can measure the work function of the sample. So this is our main motto from the KPFM. And these are the related equation with the KPFM, where as there is two types of bias is there. I said that one is DC bias, another is AC bias. So as AC bias is there, so it will oscillate continuously, and this is the laser through which it measure the topography of that means how it's moving. Okay, so as there is a capacitance, so the capacitance is generally vary with the distance with irreversibly, and the force behind this due to this capacitance is given as half DC in this potential square, and this potential is we can we can elaborate is this as this. We can take it as A and it is as B. So A plus B, the whole square formula is just it is. So this is A square and this is B square. So if we square it, B square by AC by 4 is coming, but as sin square will be there, and here from here cos square minus sin square. So from there we are getting this BAC by 4, and that cos term will get cancelled out, and this is a 2AB term.
So it has advantages over AFM.
Yes.
You can measure surface potential, which AFM can. How did they measure for solar cell? Because it is layer by layer. So how did they measure that from ETL to HTL? Because
Yeah.
Like they put it like this.
Can you explain the previous slide? 1, 2, 3, 4. Okay.
This one.
AB, yeah. This.
AB. This is the topography and CPD of a given sample, and this is the data. Okay. Yeah. And they are saying that the topography and CPD are reversible.
This one.
Yeah. So they are saying that as where the light part is there means the and the dark part here will be the opposite. Here I have the confusion actually, as here from there this data they are showing that the CPD peaks are coming at the throw, and what to say that topography means are coming around the row, means where the high is there, then the height profile is we are getting through the topography. Okay.
The position 1, 2, 3, 4.
That one is to fix.
Yeah.
Naturally, during measurement in the upper hand, one is from fixed frequency and one is from fixed temperature.
Yeah.
So when we actually measure the sample, what we fix? We fix the temperature or do we fix the?
Actually, two types of can be happen, means amplitude modification and means frequency modulation. Both can be done, but I forget which one is give more result. Means one will give higher resolution than others, but which one I forgot. This moment.
So for sample, the potential will be constant for any given sample.
For any given sample.
Like they have measured for methyl ammonium lead bromide. So how did they like find out that this is for lead
No,
bromide? And this is for-
as the means the, if one sample is there means but with the sample the CPD will change. As CPD will change, then DC phase will be changed.
No, that is okay. But I am asking how they find out that this is for the methyl ammonium and this is for the lead bromide.
Oh, they have compared with the means reference, means only taking the methyl bromide or lead bromide.
So that is what I am asking. Like
Yes.
for a particular compound is the
Yeah,
potential
means what function will be the same, no, for it.
So
Apart from that also, if you clean the surface and whatever the information you get, like the topography and the CPD, apart from that, suppose you have moisture or something that is on the surface chemistry is changing. So that's how they put that 1, 2, 3, right?
Yes.
They fix those points and they see that which one is attached. I mean, whether the water is attached, so the conductivity will definitely change, and the potential will also change in those regions. That is whether they see that whether it is on the grain or on the grain boundary. So these are the things, the pinholes, on the film. One can check by these techniques very well. And if you have a uniform film, nothing better than that. You can prove by this technique, the topography, everything. This the fluctuation. You see here, minus 0.0 to 0.0 nanometer.
Yes.
Very less. Fluctuation is very less. One can easily show by this that yes, my film is very good.
You are talking about ion microscope. So that ion microscope potential is applied on the material.
No, potential is applied on the tip.
Okay, an ion microscope, you are observing What ion migration within the material or
Oh, for that when that A is separating, then it is on the sample. That's why it is getting separated.
yes, it is in the
Yeah.
blue. This positive negative region is within the material or between the material and the thing. That means ion migration is from what to what.
Means when ion migration is means potential apply bias is there, then there will be a separation of charge
Within the material.
within the material. Now they are removing the bias, so it will come to its initial position.
And sir, can you do this kind of thing with electrolysis side? They are also apply potential. Then within the surface, what can be happening at different potential?
See, it is a time lag.
Yes.
This is the time lag, 60 seconds, one minute, 2 minutes, like that. So one thing, of course, do that. You can see the voltage change. You can fix the point. And fix the point and then vary the time. If you do at multiple locations, it will not make any sense. Okay. Fix a point, vary the time. Fix another point, vary the time. One can do it, definitely. Other questions?
But for the ion migration, they have fixed this voltage plus 2 volt or minus 2 volt. How they know that this potential should be required for this kind of migration?
I think this is a reference.
This is the reference means this is the just want to explain that if we apply this 0.2 volt, it will come back like this. And I don't know the material here.
No,
I forgot the
actually,
material.
for differentiations, the ion, for ion migration phenomena, like to happen this one, it will require different voltage.
Yes, for that is.
But all the things you cannot get in reference. I'm saying that. If you modify something, you cannot get that
Now,
reference.
here you cannot get the difference, but here it is about the time.
No, they have fixed one voltage now.
Voltage you fix,
Yeah, I am saying.
And
that
at the initial
which
time-
Which voltage one need to fix initial? That I am saying.
that's CPD that you are going to get, based on that you have to fix the voltage.
So in the previous presentation that Satya, so it was like ZNAC, CL3 heterostructure. If we apply KPFM to that structure, so we can identify.
Yeah, you can identify which one is ZNS, which one is it will have different what function.
Now you close the. He's not answering very well.